So this video is going to be about capacitors. Quick research that we did, what is a capacitor? And we found that it is a device that stores charge, electrical charge. And we have three devices that use these capacitors. You can see anything like a laptop, phone, iPad, a power bank is a really good one, and so forth. So most electronics use them. The flash in a camera uses a capacitor, builds up the charge, releases, and you get a big flash. We can use them as a battery, kind of, yes you can. There are pros and cons of using a capacitor as a battery, charging, cost, and so on and so forth. So that's an interesting idea. Some people have been using them as batteries instead of batteries, but not a lot. Okay, so so far you've done electric fields. We understand what happens to objects placed in the electric fields and how they behave and interact on surfaces like metal objects, spheres, balls, whatever. When you touch them together, what happens? All of that. Now what we're going to do is look at this practical application, and we'll understand how capacitors work, and we'll explore the different factors that affect capacitance. So a capacitor, as we mentioned, it stores electrical charge and it stores electrical energy. As a result, when you build up all the charge, you will have a lot of potential energy stored. This is the circuit symbol. Looks like a little sandwich, 2 plates. There are 3 types of capacitors, which you have as a cylinder, a sphere, and 2 parallel plates. We're going to focus on the parallel plates. This is the one that you will study. So for this parallel plate capacitor, you can say that we have 2 metal plates separated by air. You can place an insulator inside as well to make the field stronger, but we do not need to worry about that. We'll just focus on just having air inside. If you connect it to the battery, it will begin to charge. So electrons will start coming out of the battery. It will go up the wire. All these electrons are going up the wire, and then they will come up to here, and they realize they cannot go any further. So then they will start to spread out because they do not like each other. So they will spread across. And then eventually the plate will get full. Or it might not get full, I might just run out of energy, might run out of voltage, so I might not have enough strength to keep them there because they want to repel and come back. So I have to keep the battery connected. I can increase the voltage, that will force more electrons to get on the plate. More voltage means I can do more work. I can put another electron and squeeze him onto the plate and hold him there. If I disconnect this, they want to leave. So if they have a circuit to go through, they will go through that circuit. But for now, it is connected, and that means I have a negative here building up. That's repelling any electrons that were on the other side. They will come around and repel, which means only positives will remain on the left-hand side. So the electrons have been repelled from this plate. And now that I have 1 negative and 1 positive plate, you can see we have a field lines. All these electric field lines passing through from one side to the other side. Great, positive to negative. So what would happen is, if I was to stop charging it and I leave this unplugged, I unplug the battery here and over here, 2 random wires is sticking out. Electrons have nowhere to go. They are stuck in place. They cannot leave. There is no bridge. Now what I could do, if I wanted to, is I can hook this up to maybe a light bulb, and then as soon as I connect it to the light bulb, the electrons will run away. They will come through and the light will flash with light. You will have the light on while the electrons are transferring. So slowly they will leave the plate, and as they are leaving the plate, and this light will turn on, and they will join back over here. So then that means this will become balanced, and it will be back to neutral again. And then you need the battery to charge it. So that's the essence of how a parallel plate capacitor works. I've got the same thing I've said in writing here for you, so you can read this yourself. You'll find that the charge is proportional to the voltage. The more voltage you have, the more charge you can store, and the more energy you can store as well. We'll get to that though. Okay, so in an AC source, it's a little bit different, just out of interest. What happens in an AC source? The current goes backwards and forwards. If I was to use an AC source, and here is my battery, and that is my capacitor, and doing this, The current will flow this direction, that's fine. The charge will start to build. But then after a certain time, it will go back and flip over to this direction. Charge will build. The capacitor cannot hold on to any of the electrons. It will continue to charge and discharge over and over and over. So an AC, a capacitor, will not store charge, but it can be used for other features, like smoothing signals and stuff like that. It does get used, but we do not need to go into that in any detail at all. So we'll not go too much into it. This is what a little graph would look like if you did the experiment, which we did the simulation of. We investigated adding more voltage from the battery. It increased the charge, and we got a straight line going up like this. So this is what the table you would have got, something like this, and you plot them on a graph, and you will see from this graph a couple things. This line is the slope. This slope is the capacitance, the value of the capacitance. So if you ever had to find it using the slope, you can. And it's a rise over run. This is the rise, which is Q, and this is the V, and that makes sense. Q divided by V, right? Rise over run, Q over V. That's the capacitance. C equals Q over V, and that will lead us to the first formula that you need for this one. So as I've mentioned, slope, value of the capacitors. Takes us to the formula, Q equals CV. I literally just wrote that. C is Q over V, rearranged, and this is the rule for a straight line, directly proportional. Okay, Q is directly proportional to the capacitance as well as the voltage as well. A bigger capacitor means you have more space to hold the charge. Of course, there will be more charge. Bigger voltage means I have more energy to put the charges onto the plate. Then, of course, more charges will be on the plate. Makes sense. Then we investigated the different parts of a capacitor, the separation distance, the area, and we found the different effects they made. We realized that if I have a bigger area, that means there is more space. It's like having a bigger room, which means you will have more capacitance, which means you can store more charge, because remember, Q equals CV. So if my C gets bigger, that means I will have more charge. Makes sense. And what about my distance? If I take my distance and I make the distance bigger, the electric field between the two plates have further to travel. There will be less repulsion between the two plates. Like for example, if I had a big gap between the plates and I had a small gap between the plates. And this is one side is positive, this side is negative, and this is positive, and this is negative. You'll realize that if you have a bigger distance, you will see that the capacitance will be reduced. Closer distance, this means this can increase my capacitance because it's stronger electric field. So if I increase the distance, my capacitance will decrease. That's important to know. That means I will store less charge if my capacitance decreases. So that's one thing to think about when using this formula. Okay, so this epsilon naught is the permittivity of free space. We've used it before already. It's the same number we're going to use because inside here is air. So we'll just keep that as 8.85 times 10 to the minus 12. Area is the plates in meters squared, and we have the capacitance in farads, distance in meters. And you may need to derive this epsilon naught. We can start with the formula C is Q over V, and instead of writing V, we can write ED. So we have Q over ED. And if you remember the density formula, we can put the density instead of the electric field. We can density over epsilon naught. And then we can put this into here. Density formula, Q over A. We still have the epsilon naught. And we can simplify it a little. We can get rid of some of the Q's because Q over Q cancels. Can bring the A up to the top. It gives you the EA over D. Not too important to derive, but it is there if you need to do it. Okay, so now we know capacitance is the ratio of charge to potential difference. And the unit of capacitance is, of course, the farad. And 1 farad is the same as 1 coulomb per volt because of the formula. And it's usually quite a big number, so we won't really ever see 1 farad, 2 farads. It's usually small numbers like times 10 to the minus 6, minus 9, and so on. So we did some practice questions on this. We have a charge that's stored, so Q equals CV, solve it, and you'll get the answer. 1.25 times 10 to the minus 2 is the same as saying 0.0125. We did some concept questions on this one. This is when taking the formula, when you compare them. I'll do this top one here for you. A parallel plate capacitor has C. A second one has twice the area, half the separation. So I'll also do C, E, A over D. If I set everything to 1, it'll be 1 times 1 over 1, which is simply 1. Now what I can do is I can change it. I can say second plate has twice the area, so 1 times 2, half the separation, 1 over 2. And what happens then? So that's 2 divided by a half, that becomes 4C. I have increased by 4 times, or for 4C. You can use that rule to help you with other questions as well. So when we looked at combining capacitors in series and parallel, we noticed a few things. In series, we realized, first of all, the voltage is shared between them. This is something we already know from the beginning, from grade 9 and 10 when you did series circuits. The voltage is shared between all the parts. The charge ends up being the same on each one. So you have the same charge here, here, and here, because there's only one path to follow. Like the same idea as current. Current will follow one branch, so if I have 3 amps coming here, 3 amps worth of charge, so that will be the same charge gets distributed across in the same circuit. So you can use the rules Q equals CV to find the total charge, and you will know the charge in each capacitor. You can divide it by 3 because it's 3 capacitors. To find the capacitance, you do the 1 over C1 plus 1 over C2 formula, put it in your calculator. You flip both sides, and then you can get the answer. Or, if you want to go directly to the answer in your calculator, you can do this, put it in a bracket to the power of minus 1. Directly, you will get your answer for C. A little quick tip there for you. So, good point here is that the resulting capacitance is always smaller than the smallest capacitor. If I have 2 only, it'll always be half of the 2 values, assuming that they are the same. But you can figure them out when you use your calculations. For parallel, a little bit different now. Voltage is the same in each branch. Each electron coming through here has the voltage of whatever the battery is supplying it, and each electron, and they all run into one capacitor each. So that will have the full voltage. The charge gets split into 3 branches, so you add the individual charges together, and the capacitance can easily be added because it's equivalent of having one big plate. You have all the space, add another one, you have more space, add another one, there is more space, so you have more capacitance. The charge will be greater, the capacitance will be greater. A couple of concept questions here that we did in class, and a couple of calculations based on the circuits to find the total capacitance and the energy stored, or in this case the total charge stored. If you wanted to find it, well, for example, these are 3 in series, so you do 1 over this plus 1 over this plus 1 over this, you get your answer. And if you wanted to find the total charge, you do Q equals CV, whatever you calculated multiplied by the voltage. And then looking at the right hand side, we have 2 in parallel, 10 and 10, and they are in series with this one and this one. So we'll do 10 plus 10, that's 20. So then after that you'll do 1 over 20 plus 1 over 20 plus 1 over 20, and you will get 3 over 20. Flip it, and you get the total capacitance. And you can find the charge the same way. We did more practice with complex circuits. We went through this in class, and then we moved on to the energy in capacitors. We know that energy is usually work is Q times V. That's great if we have a constant voltage and a constant charge. Capacitor is building up charge as Q equals CV. So that means if I'm charging the capacitor, you will see this graph. So rather than doing Q multiplied by V, this multiplied by this, I have to take a half of it because it's a triangle. It ends up being a triangle. Otherwise, it would have been a nice little rectangle, Q times V, you would have everything. But because it's a capacitor, you have to take half of that. So that's where the rule E equals area under the graph, a half QV. This is the big rule here. You can combine this with Q equals CV. The Q equals CV. You can combine this formula. Instead of Q, I can write CV. CV multiplied by V will give you CV squared. And then a half Q squared over C. If I rearranged it to replace V, I can do V equals Q over C. So Q multiplied by Q over C Q squared over C. That's how you find the energy stored in a capacitor. Couple of practice questions that you did, and that was it. Thank you.